Welcome back to the Algebraic Graph Theory seminar. This week we have Tom Wong talking about equivalent Laplacian and adjacency quantum walks on irregular graphs.
All right, thank you. So just so that you know, I do have the chat window open on an external monitor, so I can monitor that. So if you have any questions along the way, feel free to either ask questions in the chat or just unmute yourself and let me know. So this is joint work with Josh Lockhart, and we actually just posted this on the archive 2 weeks ago. So we're really excited to share this result with you today. So normally I'm a physics professor at Creighton University in Omaha, Nebraska, but this summer I'm visiting the Laboratory for Physical Sciences. That's where I am right now. That's this office behind me. It's not my usual office. All right, so I'm going to start off by talking about the two types of quantum walks I'll be comparing, which are called Laplacian quantum walks and adjacency quantum walks. I understand that a lot of people in this group have actually worked on these types of quantum walks before, and so hopefully this isn't too elementary, but I'm actually going to introduce these from the perspective of a physicist, because I am a physicist, so hopefully you might find that a little interesting. And then I'm going to talk just very briefly about some of the differences between these two types of quantum walks. And then we'll start talking about how they can be equivalent to each other in different circumstances. So one is a very well-known result that they are equivalent on any regular graph. And then we're going to jump into our contribution with this preprint, which is that they can actually be equivalent on irregular graphs. And so I'm going to go into some of the history of this by looking at a graph with 6 vertices, because Josh actually brought this up to me back in January of 2016, so over 5 years ago. And it's only recently, within the past year, that we made some significant headway that led to writing this paper. And so I think the history is kind of fun and interesting. So let's talk about that. And then we'll look at this equivalence on irregular graphs with 11 vertices or less. And then from that, we actually identify 8 families of irregular graphs where there's this equivalence. And so, and then I'll end with some open questions. Okay, so let's go ahead and start by talking about what a Laplacian quantum walk is. So as a physicist, when I think quantum mechanics, the equation that comes to mind is Schrodinger's equation. It's the fundamental equation of quantum mechanics. And so it's I(h) bar times the time derivative of psi is equal to the Hamiltonian times psi. So I is just the square root of -1. H bar is Planck's constant over 2 pi. It's just some number. Psi is your wave function, which is basically when you take the norm square of it, gives you your probability distribution for where you'll find your quantum particle. And then H is the Hamiltonian. So the Hamiltonian actually has physical meaning. It's an operator that corresponds to the total energy of the system. So depending on what physical system you're looking at, the terms might be different, but they're all going to have a kinetic energy term and perhaps a potential energy term. So the kinetic energy has a specific form in quantum mechanics. It looks like this. It's minus h bar squared, that constant h bar again, divided by 2 times the mass of the particle, times L, which is in physics, we typically write it as del squared because it's Laplace's operator, or the Laplacian. And so in Cartesian coordinates, it would just be the second order differential operator. Again, if you're familiar with del, which is the gradient operator, it's just del dot del. So that's why we typically write it as del squared. But I understand in the math community, you typically will write it as L. So that first term there, minus h bar squared over 2m times L, this is the kinetic energy. And then for a quantum walk, we're just gonna make the potential energy 0. So there's no other external forces that are affecting your randomly walking particle. So to write this a little more simply, so that we don't have to keep writing h bar squared over 2m, I'm just gonna write h bar squared over 2m as gamma, so that the Hamiltonian is minus gamma L. Okay, so in quantum mechanics, if you have a randomly walking particle, or like a free particle that's free to move around, it just evolves by Schrodinger's equation. And then the Hamiltonian is minus gamma times the Laplacian. And we can do this exact same thing on a graph, and that will give us a quantum walk. So let's see, how do we do this on a graph instead of in like XYZ coordinates in in R3 space. So if we're on a graph, such as this graph here with 4 vertices, then instead of a wave function that is over all of 3-dimensional space, our quantum state is going to be a superposition over these 4 vertices. So there's going to be some amplitude C0 of being at vertex 0, some amplitude C1 of being at vertex 1, some amplitude C2 of being at vertex 2, and some amplitude C3 of being at vertex 3. So we're superpositioned over these 4 vertices. And we can write this as a column vector with these 4 amplitudes. So this is what the quantum state looks like. And the Laplacian now, instead of being that differential operator in terms of x, y, and z, it's going to be the Laplacian of a graph. And the Laplacian of a graph in the physics sign convention, I know mathematicians like doing the opposite sign convention. In this physics sign convention, that way it matches the stuff from the previous slide. It's going to be the adjacency matrix minus the degree matrix. So the adjacency matrix has a 1 if 2 vertices are adjacent to each other, and then a 0 otherwise. And the degree matrix just has the degree of each vertex on the diagonal. So vertex 0 has 1 neighbor, so it has a 1 here. Vertex 1 has 3 neighbors, so it has a 3. Vertex 2 has 2 neighbors, and vertex 3 has 2 neighbors. So the Laplacian is just the difference of these 2 matrices, which is this. So this is the Laplacian now, which goes into that kinetic energy operator in the Hamiltonian. And so a Laplacian quantum walk is just evolution by Schrodinger's equation with this Laplacian and with this type of state. That's just a vector. And so to write things a little more cleanly, we're going to go ahead and set work in units where h bar is equal to 1, and we're going to set gamma equal to 1 as well. And if we do that, the Schrodinger's equation is now I, and h bar is now 1 times the time derivative of the state is equal to h times your state. And then the Hamiltonian is, and it was minus gamma L. If gamma is 1, it's just minus L. And so if you solve this differential equation, you just get that the state at time t is equal to e to the ILT times your initial state. So your initial state is going to be some vector of length 4. This is a matrix exponential because L is a 4x4 matrix. And then whatever vector you get is going to be the state of the system at time t. And so this is what we're going to call a Laplacian quantum walk, because this quantum walk is governed by the Laplacian. All right. So we can do a similar thing, but instead of the Laplacian, we'll get the adjacency matrix by itself without this diagonal degree matrix. And so let's see how we can arrive at that. So we're going to look at another physical system. It's quantum mechanical again. And it's going to be a network of spin 1/2 particles. So an electron is an example of a spin 1/2 particle. So you can think of it as this is a network or a graph of electrons. And so here I just have 8 electrons and they're drawn in this grid. And so if you want to look at the interactions between these spins, the Hamiltonian from some physics stuff will look like this. So the Hamiltonian is equal to minus 1/2 times the sum over all pairs of these spins times the adjacency matrix. So the idea is we're restricting ourselves only to nearest neighbor interactions. So the adjacency matrix will ensure that. So if they're not adjacent to each other, then this term will be 0. So there won't be any interaction. These terms Jx, Jy, Jz, these are couplings that determine the strength of each direction of spin interaction. So those are just numbers. And sometimes some of them could be 0. And then x, y, and z, these are the Pauli matrices. So xi would be the Pauli X matrix acting on spin I, and then this would be the Pauli X matrix acting on spin j. And so here we have 8 spins. And just to remind you, the Pauli matrices, x is the NOT gate in quantum computing. It flips 0 to 1 and 1 to 0. Y is similar to the NOT gate, but it has a phase component to it. So y turns 0 into 1 with a phase of I, and y turns 1 into 0 with a phase of minus I. And z is just a phase gate. 0 stays 0, but 1 gets a phase of minus 1. So these are just your Pauli matrices. And we're going to look at a specific interaction where Jx and Jy are both equal to 1, but Jz is 0. So we're not going to have any z interaction in the spin, so that the Hamiltonian looks like this. Okay, so this is a physical quantum mechanical system, and some of the physics, if you didn't follow, it's okay. The point is, like, there's a physical system where you have this Hamiltonian, and this Hamiltonian, as we'll see on the next slide, will give us this other type of quantum walk. And so we get this other type of quantum walk by looking at the subspace of single excitations. So basically, we're going to be looking at this basis where only one of the spins is a 1 at a time, and the rest of them are all zeros. So if we do that, we can look at what the Hamiltonian is going to be in this basis. So this is the Hamiltonian that we had from the previous page. And if we want to look at its elements, say that its RS element, that would just be the inner product of this Hamiltonian with whichever elements we're looking at. So if we want to know like the 1, 2 element, it would just be on the left, we'd have this state, and on the right, we'd have this state, and we're taking this inner product. And so if we plug in this Hamiltonian and we distribute this R and S inner product, we basically get this here. And so if you look at these inner products, most of the time they're going to be 0, but you're going to get 1 when R is equal to I and when J is equal to S. So the reason for that is, let's say R is 1 and S is 2. So we're looking at these two basis states. This X gate will turn a 1 into a 0 and a 0 to a 1. So if this X gate happens to flip this 1 to a 0, then this becomes all zeros. And if this other X gate happens to flip this 1 to a 0, then this becomes all 0. And now you're taking the inner product of the all 0 state with itself, which gives you 1. And so that's when this is equal to 1. And otherwise, the 1 is not going to match up in terms of its position. And so you're going to get 0 all the other times. So this is 1 when R is equal to I and when J is equal to S. And so writing this using the Kronecker delta, it's just this is 1 when R is equal to I and this is 1 when S is equal to J. And the same thing actually happens with these Y gates. So when you apply a Y to a 1, you get a minus I. And yeah, so basically you what happens is that your phases end up canceling out, and so you get another 1. And so what you get then is that when R is equal to I and S is equal to J, this becomes 2, which cancels out with a 2.5 in the 1/2. So you get a minus times the adjacency matrix. So basically, the Hamiltonian is just equal to the minus of the adjacency matrix. So if you didn't follow any of the previous stuff, which is, I know I had a lot of physics stuff and I'm kind of referencing quantum gates and stuff, basically, this is the main conclusion. There is a quantum mechanical physical system where the Hamiltonian is equal to the negative of the adjacency matrix without the diagonal degree matrix. And so so if you evolve by Schrodinger's equation with this Hamiltonian, the evolution looks like this. So instead of e to the ILT, you get e to the IAT times your initial state. And so this is another type of continuous time quantum evolution that we call an adjacency quantum walk, because now it's governed by the adjacency matrix instead of by the Laplacian. And so we have these two different types of continuous time quantum walks, and we're going to be exploring these two types throughout this talk. If you have any questions, feel free to chime in. All right, so I'm going to spend one slide just going over a couple of differences between these two walks, because you might imagine that, if this walk is governed by the Laplacian, this walk is governed by the adjacency matrix, that they're going to evolve differently. And that is true in many circumstances. So one example where this comes up is when you look at perfect state transfer, which the people in the audience actually know way better than I do. And specifically, if you look at paths, if you evolve using this Laplacian quantum walk, you only get perfect state transfer on the path of length 2. So if you start at vertex 1, you get perfect state transfer to the other side if it's length 2. If it's any longer than that, you don't get perfect state transfer from end to end. Whereas if you do a quantum walk with the adjacency matrix, you can actually get perfect state transfer for both P2 and P3, and then on nothing longer than that. And so this is a clear difference between these two types of quantum walks. Here you only get perfect state transfer in this case, and here you get perfect state transfer in both of these cases from one end to the other. So that's a qualitative difference. There was a question whether there are other quantum mechanical models that use other matrices related to a graph. So yeah, I've introduced that there's these two models. And these are the ones that I know the best. I mean, there are some slight changes to these, like you can look at weighted graphs as an example. There's been some work where people have looked at graphs where the adjacency matrix has a phase of, like, say, e to the I theta going one direction and e to the minus I theta going the other direction. And so there are some other ones in terms of like completely different matrices. I don't know if there's any other commonly used ones besides these two. There might be, but my knowledge is focused on these. So actually, if anyone knows of other ones, you feel free to. Yeah, so signless, Laplacian normalized, Laplacian. Oh yeah, great. So there's some other ones. Yeah, so thank you for contributing those. So when someone said is instead of doing A minus D, you could do A plus D, and then there's normalized Laplacians as well. Another question is, what's the physical model for the Laplacian walk? It's basically any quantum evolution where the particle is walking in discrete space. So the kinetic energy of the particle, like the motion of the particle, naturally gives rise to this type of Laplacian quantum walk. Because remember, the Laplacian is proportional to the kinetic energy. Thank you for those questions. Yeah, so whatever your Hamiltonian is, it has to be Hermitian, meaning that it's equal to its conjugate transpose. And if it's Hermitian, then e to the I times that Hermitian matrix T, then this exponential will be unitary. Yeah, so the condition is that the Hamiltonian needs to be Hermitian so that this exponential is unitary. Good question. Yeah, so both of these are Hermitian matrices. So these are valid quantum evolutions. Thank you for the questions. Yeah, feel free to keep on adding to the chat there. So another difference between the Laplacian and adjacency walks arises if you look at search on the complete bipartite graph. So here's a complete bipartite graph. And this is actually something I looked at with some collaborators back in 2016. And so if you want to do search on this with the Laplacian, then you can actually show that it's best to start in a uniform superposition over all of these, say, 7 vertices. So the initial amplitude is 1 over square root of 7, 1 over square root of 7, 1 over square root of 7, and so forth for all of these. And if you evolve with a Laplacian quantum walk with a search oracle, then what your final state is either going to be a uniform superposition. Actually, I should clarify. So in this picture here, you see how there's these two A vertices have double circles, and this B vertex has a double circle. These are your marked vertices that you're trying to find. So the idea is you start in some superposition over everything, and then you try to converge on those marked vertices that you're searching for. And so if you search with a Laplacian quantum walk, then depending on what jumping rate you use, you'll either converge onto the A marked vertices alone or the B marked vertices alone. So basically, you can only search for the marked vertices in one of your partite sets at a time. And that's an interesting behavior of that search algorithm. If you search using the adjacency quantum walk instead, it turns out it's better to start in a weighted superposition. So the amplitudes on the left side will all be equal, but they'll be different from the amplitudes on the right side, which will all be equal to each other on the right. If that makes sense. So the left side is not going to have the same initial weight as the right side. And this is basically to make it so that your final state has a success probability of 1. That's why they have different initial states. So if you evolve using a search algorithm with adjacency quantum walk, then your final state, instead of being just A or B, it's actually going to be a superposition of A and B. So your final state allows you to search for both, for marked vertices in both partite sets. Instead of over here, you can only search for marked vertices in one partite set at a time. Yeah, so this is another qualitative difference between these two types of quantum walks. All right, so despite these differences, there are cases where the quantum walks are equivalent. And the big example is if you have a regular graph. So let's say we have a regular graph with degree D, so all the vertices have D neighbors. I feel a little dumb saying that with this math crowd where people do algebraic graph theories. Like, of course, you know what a regular graph is. But anyway, so let's see what happens to the Laplacian if we have a regular graph. So this degree matrix D now is just going to have lowercase d all across its diagonal, because again, every vertex has lowercase d neighbors. So this degree matrix is now going to be little d times the identity. So that way it has little d across the entire diagonal. So again, this Laplacian is a minus d times the identity. So let's see how this affects the evolution. So if you look at the Laplacian quantum walk, the state at time t is just e to the ILT times the initial state. And so if we plug in L as a minus di, we get this line, just literally plugging in a minus di. And since the identity commutes with everything, we can write this as two separate exponentials, as e to the IAT and e to the IDIT. And then e to the IDIT, because I is the identity matrix, this is just going to be e to the IDT. And I put it right here, e to the IDT, because identity is not going to do anything. So basically what we get is we get a phase. This is just a number now, e to the I lowercase dt, times this matrix exponential with the adjacency matrix in it, times your initial state. And this here, this is just your adjacency quantum walk. So this is the state of the system that you get with adjacency quantum walk. And this phase here, this is a global phase. So in quantum mechanics, global phases can be dropped because there's no physical significance to it. And so basically we can drop this global phase, giving us just this remaining term, which is exactly the state that you get with adjacency quantum walk. And so what we see is that for a regular graph, the Laplacian quantum walk is equal to the adjacency quantum walk, because you can drop this global phase that appears. And so if you have a regular graph, the Laplacian and adjacency quantum walks are equivalent. And so this idea of writing the degree matrix as some multiple of the identity when it's regular and then leading to a phase you can drop, this appeared in an early paper by Charles and Goldstone back in 2004. Although they weren't thinking about the equivalence of the Laplacian and adjacency walks, but this falls very naturally from this observation that you just get a global phase. All right, so now to start with our new contributions in this preprint. So this goes back, as I mentioned, in January of 2016. So I was at the QIP conference in Banff, Canada, about over 5 years ago. And that's where I met Josh Lockhart. And so he brought up to me that he found some irregular graphs where these two quantum walks are the same. And I was like, oh, like you mean regular graphs, right? Because obviously irregular graphs are equivalent. Like, what do you mean like irregular graphs? I thought maybe he misspoke. But he's like, no, like these are irregular graphs. By the way, these are not direct quotes. This is me trying to remember what happened, 5.5 years ago. So, the actual words are different, but this is what I remember the sense of the conversation was. And so when he says like, oh, irregular graphs where these walks are the same, I'm like, I don't see how they can be the same. Like, you're not going to get this global phase you can drop, and it seems like you should get very different evolutions. And he's like, let me, I did some simulations and I found a couple of graphs. Let me find them for you. And so later in the conference, I don't remember if it was the same day of the conference or another day, but he basically gave me this graph with 6 vertices. And what he said is that if you start at, say, vertex 1, so at one of the two ends, to start, say, at vertex 1, meaning the initial state is just vertex 1. So as a 6 by 6, sorry, so if as a vector of length 6, you just have a 1 and then zeros everywhere else. What Josh said is that if you start at this vertex and you evolve by the adjacency and quantum walks, that they evolve equivalently. And so I was like, okay, well, this is pretty easy to do. The adjacency matrix of this graph, you can just write down very easily. Then the degree matrix is just this thing, because vertices 1 and 6 have 2 neighbors. All of these middle vertices have 4 neighbors. And if you subtract these, you get the Laplacian. And now I can just do a very simple matrix exponential times this initial state for the Laplacian walk and for the adjacency walk. And I can just do this numerically just to double check to see if these two walks are indeed equivalent. And so that's what I went ahead and did in Mathematica. So I picked a value for time. Let's say time is equal to 7. So if you use the Laplacian quantum walk, you find that the state at time 7 is this thing. So there's your 6 amplitudes. So this is the amplitude at vertex 1, amplitude at vertex 2, 3, 4, 5, 6. And if you do the adjacency quantum walk, you get this state. And so at the time I looked at these, I was like, these don't look the same, Josh. Like, I don't see how these are equivalent to each other. So I was like, okay, Josh, I must be making a mistake. I'm getting different evolutions. And then Josh clarified, like, oh, he wasn't considering the state. He was looking at the mod squared amplitude or the probability distribution. Oh, okay. So you were looking at the probability distribution, because if you're actually measuring the quantum walk, what you care about is the probability. So you can do is take the norm square of each of these elements, and the probability distribution of the Laplacian quantum walk is this. And again, if you take the norm square of each of these amplitudes, the probability distribution of the adjacency quantum walk is this. And now you can see they are the same. And so it's like, oh my gosh, Josh, like this is so obvious that you should look at the probability distribution, but I had totally missed it. So it's kind of like mind blown of how simple yet clever this observation was. And so, of course, you try this at time equals 7, you try other time is equal to 1, time is equal to pi, time is equal to 100. You try different times and you see that you keep getting the same probability distributions, doing this numerically. But then I tried some really big times. Let's say time is 10 to the 12th. So this is a ridiculously big number. You do the same thing. You can find the state of the Laplacian quantum walk and the state of the adjacency quantum walk. Take the norm squared of each element to find the probability distribution. And you get this for the Laplacian walk and this for the adjacency walk. And if you look at these closely, they actually now start to differ a little bit. So for example, the probability at vertex 1 is 0.168373. This is 0.168422 instead of 373. And you see for all of these, they actually differ a little bit. And so now it's like, like, are they actually the same, or are they? So obviously they're slightly different, but because we use a time that's so big, you have to wonder, are they different because there's actually numerical error now in our calculation? So are these actually the same? And any difference we see is due to numerical error, or are these actually different? And in fact, this graph does not have equivalent quantum walks for all time, or for any time for that matter, because all we've done is we've simulated things numerically. This is not a proof, as the people in this seminar would know very well. So basically, we need a proof before we can determine if these are actually equivalent or not. And so the steps to do that are pretty straightforward. The idea is you can find the eigenvalues and eigenvectors of, say, the Laplacian first. Once you have the eigenvalues, we'll call them lambda 1 through 6, because there's going to be 6 of them, and eigenvectors psi 1 through psi 6. You can then express your initial state as a linear combination of these eigenvectors. So I'll call these coefficients C1 through C6. So again, it's just a linear combination of these eigenvectors. That way, we can easily find the state of this system at time t. You get the state of the system at time t just by multiplying each eigenvector by e to the I lambda t by its eigenvector. Because remember, the evolution is e to the I LT. So this is an eigenvector of L, then you just get its eigenvalue there. And similarly for all of these. Once you have the state of the system at time t, you just take the norm square of each element to get the probability distribution. So this is how you can analytically find what the probability distribution is at time t. And you do the same thing with the adjacency quantum walk. And now that you have these two analytic expressions, you can just compare them now and see, are they the same or are they different? Rather than using numbers where it's clear that we might be having some numerical error. So yeah, the goal is to compare them. So I went ahead and did this again back in early 2016 when we first started exploring this together. And so using Mathematica back then, 5.5 years ago, I calculated the probability at vertex 1 at time t. So for the entire probability distribution, you need the probability at all 6 vertices. This is just the probability at vertex 1. And this is what I got from Mathematica. So this is the probability at vertex 1 using the adjacency quantum walk, and this is the probability at using the Laplacian quantum walk, again at vertex 1. And so for the walks to be equivalent, these two expressions should be equal to each other. And if the walks are actually different, then these two expressions should be different. And if you look at them, they're kind of hard to compare. For one, they have different overall phases that Mathematica has factored out. And then the ordering here is not the same as this ordering here. And it's just a mess, right? It's not immediately obvious. You'd have to actually manually go through and kind of compare each element and tinker with it. And also these are the probabilities at vertex 1 with each quantum walk. So both of these should actually be real numbers. And we see that Mathematica has still left it at these complex exponentials. So you might want to convert these into, write them as real expressions. And so it's like, this is going to be a little tedious. And so basically, I was hoping to just get it right out of Mathematica, but wasn't able to. And so it looks like I'd have to do some work by hand. And basically say, no thanks, that just looks rather tedious. It's like, it's doable, but like, do I want to do it right now? Not really. And so basically, we ended up putting it off for 5 years, right? So one reason for not doing it is that it's tedious. Another thing is the expressions I showed you from Mathematica, that's only the probability at vertex 1. You also have to show that the probability at all the other 5 vertices are equal. So that way your entire probability distribution is the same. And so it's like, you actually have to do what was on the previous slide like 5 times to work it out by hand. It's just like, I've got other projects to work on. I had plenty going on at the time. There was no shortage of research projects for me. And so I was like, I'll just put this off. And this is actually a pretty straightforward problem, just some linear algebra. It's tedious, but it's straightforward. So this would actually be a great project for a future student. And at the time I was a postdoc. And so, I kept this project in mind for future students for when I'd eventually find a faculty position. And so basically from 2016 until we picked this up again in last October, this project kind of went dormant. I thought about it from time to time. I was like, oh, this might be good for this new student that I have. But then actually I ended up assigning those students different projects. So starting in 2017, I started a faculty position and did have students, but I just ended up giving them other projects just because of what they sounded interested in. And so basically this project kind of was on the back burner. And so in October 2020, I thought of this question again, and I reopened the Mathematica notebook. And also all my students were working on other things. And this was something where it's like, if I looked at it again, it wouldn't compete in a sense with the projects my students were working on. Because I want my students to kind of take ownership of their projects and be able to solve their projects themselves. So I revisited this and pulled up that old Mathematica notebook and just reran it using a newer version of Mathematica, because it was now 2020 and I'd upgraded Mathematica several times since then. And when I reran the notebook, this is what I got for the adjacency quantum walk and the Laplacian quantum walk, again for the probability at vertex 1. And if you look at these two results to see if they're the same, what do you see? you see now very clearly they are exactly the same. So just by updating Mathematica, basically from 2016 to 2020, Mathematica is now simplifying expressions slightly differently, and we actually find that they exactly match. And similarly, if you look at the probability at all of the other vertices, they also match. And so this isn't very clean because these are all these complex exponentials when they should be real expressions. But basically, we've proved analytically that the probability distributions of the two walks are identical for any time t. And so we actually do have irregular graphs on which Laplacian and adjacency quantum walks evolve the same way, in the sense that they have the same probability distribution. And so that was pretty exciting. And so that opened up the door then for the search for more. So if we know there's one graph that Josh gave me with 6 vertices, very, basically ask, are there other irregular graphs where we have these equivalent quantum walks? And so we decided to search for more. And so I decided to search for all graphs up to 11 vertices. And that's because all the graphs are available on Brendan McKay's website. And so basically you can download a list of all connected graphs up to, up to 11 vertices. And so you can see that it gets pretty big. Like with 11 vertices, there are, this little zoom thing is in the way. There's over 1 billion connected graphs with 11 vertices. With 10 vertices, there's 1.1 million. No, sorry, there's 11 million, 11.7 million, and so forth. And so, okay, I was gonna have to simulate all of these to see if I can find graphs where we think the two types of quantum walks evolve the same way. And so this is gonna take some time. So I coded up some, so I wrote some code in Mathematica to go through and to simulate all of these over a billion graphs. And I started it on my laptop. And then I quickly realized from the progress I was making that it was gonna take my laptop about 70 days to do. It's like, I'm not leaving my laptop on for 70 days, just crunching this thing. And, it's just not gonna happen. And so I thought about it. So at Creighton, I have my research lab, which is just a bunch of computers because I'm a theorist. But I was okay, if I take all of my computers in my research lab and they all have multiple cores, so use every core of every computer in my research lab, which equated to about 20 cores total. It's like, how long will this take me? Well, it would take about 3.5 days. So it's like, that's doable. And so I went in over break because at this point, even though it's early December, because of COVID, we ended the semester by Thanksgiving, by like late November. So at this point, it was like winter break, an extended winter break. And I decided to spend my extended winter break working on this research problem. So into my lab, started everything running, and then came back a few days later and got the results. And so here are all the graphs up to 11 vertices where you get equivalent quantum walks. And I don't expect you to be able to see this, but the point is there's a bunch of them, and there's actually 64 of them. And so we're going to be going to these in more detail so that you can see them. But first, here's a table showing the number of them. So here we have the number of vertices. So for example, if you have graphs with 7 vertices, there are 853 simple connected graphs with 7 vertices. Of these 853 graphs, 4 of them are regular and 849 of them are irregular. So these are the ones we want to search. We want to search all the irregular ones. And we found there's only one graph of 7 vertices where the walks are equivalent. With 6 vertices, there's only one. That's the one that Josh had found. There's also one with 5 vertices, actually, which I thought was interesting. So there's actually a simpler one than the one that Josh had originally found. If you go up in vertices, 8 vertices is 4, with 9 vertices is 6, with 10 vertices is 23, with 11 vertices is 28. And then, so there's a total of 64 here. There's a question of, do these graphs depend on which target vertices we choose? So you'll see in the pictures, I will actually show what your starting vertices can be. Basically, we use every single vertex as a potential starting vertex, and we see, does that graph have one where the walks are the same? This one with with 6 vertices that Josh proposed, we proved that, and I showed you a very dirty proof in Mathematica. In our paper or preprint, we work it out very nicely. We also proved the example with 5 vertices, and then the rest of these are all just based on our simulations, because it's like we're not going to go through proving all 64 of these. Clearly, there needs to be mathematicians that can prove this more systematically, and that's why I'm really glad to actually be sharing this with you guys, because I feel like you guys actually have the skills that I don't have to take this research further. But let me talk about that graph with 5 vertices first, just to because there's another proof approach that we explored in our preprint. So the graph with 5 vertices looks like this. So you see it's very similar to the one with 6 vertices that Josh found, except the one with 6 vertices that Josh found stuck out on this side as well. So there's like a little triangle sticking out here. So basically, if you chop off that triangle, you get this graph with 5 vertices. And these red vertices, 1, 4, and 5, those are the starting vertices. So if you start at vertex 1, the walks are equivalent, or if you start at vertex 4, the walks are equivalent, or if you start at vertex 5, the walks are equivalent. And actually, if you look at this graph, you'll see that those vertices are isomorphic to each other. They have the same structure, because you can imagine you have these 2 vertices, 2 and 3 in the middle. Then 1 is adjacent to both of those, 4 is adjacent to both of those, and 5 is adjacent to both of those as well. So you see that 1, 4, and 5 are all kind of, they have the same structure and how they're connected to 2 and 3. So you can prove that vertex 1 works, then the other ones work. And it looks like there's the math term is that they are co-spectral. So thank you for providing that term. I did not know that. Again, I'm a physicist, not a graph theorist. So, okay, so one way of proving this is just like we did with vertex 6. You can just, start at each vertex, evolve, and take the norm square of the final state. Another way to explore this is something I learned actually from you guys from going to workshops that you guys have organized. So you guys, I mean like the Waterloo group, Chris Godsell and his extended network of students and alumni and collaborators. So another way is using the mixing matrix. So I learned this from you guys. And so the mixing matrix, what you do is you look at the time evolution operator. So for the Laplacian quantum walk, it evolves by multiplying the state by e to the ILT. So what you do is you take this matrix that I'll call capital U, and you multiply it by element-wise by its complex conjugate. And when you do that, you get a matrix that looks like this, where A, B, C, and D are too long to fit. So I just, I wrote them down here separately. And this has a physical interpretation. The first column is the probability distribution if you start at vertex 1. The second column is a probability distribution if you start at vertex 2, if you start at vertex 3, 4, and 5. So this is basically working out all the probability distributions at once. This is with the Laplacian walk. You can do the same thing with the adjacency quantum walk. Its time evolution operator is e to the IAT. And so you can calculate its mixing matrix. And what you get is this, which looks very similar, except you have E and F, which are these down here. So they're different kind of in these 2 columns. But the main idea here is that if you compare these columns, you see how column 1 and column 2 are identical. That means they have the same probability distribution if you start at vertex 1. So that proves that they're equivalent. That you have equivalent quantum walks when you start at vertex 1. Similarly, if you compare columns 4 and 5, they're identical. So you get the same probability distribution when you start at vertex 4, so the walks are equivalent. And same thing with column 5, you're going to get the same distribution when you start at vertex 5. And so this proves all at once that the walks are the same when you start at vertices 1, 4, or 5. So this is another approach that you could take to proving these. But this is the end of our proofs. We only did, again, the 5 vertex example and the 6 vertex example. So let me just tell you what the other ones are. The distributions are the same if you account for the starting vertex. So here, if you start at vertex 1, then the probability at vertex 1 is A. Here you start at vertex 4. So you see how A is down here, and here you start at vertex 5. So A is now down here. So basically, these are the same distributions, but you have to shift the labeling. Does that make sense? I'm sure there's a graph theory term for this. All right. Good to see that my hand wavy explanation made sense. Okay, so let me present to you the graph. So here's the one with 5 vertices. Here's the one that Josh found with 6 vertices. And you see I made both of these red because you can start at either end and you'll get the same. You'll find that the walks are the same. Here's the one with 7 vertices. With 8 vertices, there's 4 different graphs. They look like this. Obviously, we have 64 graphs total, so you're not going to absorb all of these just by me clicking through them, but they're all in the preprint, so you can look back more carefully. But hopefully you can get a little feel for what these might look like. With 9 vertices, we have 6 different graphs. So here's the 6 graphs with 9 vertices. And then with 10 vertices, we have 23. So I needed 2 slides for this. So here's the first slide. I'll wait a little bit. Maybe I should say these are screenshots straight from the paper. So these labels A, B, C, D, E, F, and so forth, these are all matched with the paper. So you can go back and refer to any of them. Here's more graphs with 10 vertices, the rest of them. So these are not the order that Mathematica found them. I reordered them to kind of try to group them into similar looking graphs and to make them fit on the pages of the preprint. All right, and then with 11 vertices, there were what, 28? What was it? I'm guessing. Where's that table? Here we go. There were 28. Okay, yeah, with 11 vertices, there were 28 of them. So here's the first page. And then here is the second page. And that is all 64 graphs. And so it's very reasonable to ask, by looking at all these graphs, and you might have been looking for these, are there any patterns or are there any generalizations? And so that's what we looked at. And so yes, we found 8 different, what we're calling families of graphs, and there's probably more. It's basically, I don't know if you remember that first picture I had where I printed all the graphs and cut them out and put them on a table. That was so I could like rearrange them and like look for patterns and stuff. And so it was just me. We found these 8 by me eyeballing them and looking for patterns. So I'm sure there are more. So this is an open question. You know, are there other families of these? So here's the first family. So let me show you where it comes from. So looking at the 64 graphs we just had, here's the one that Josh found. Here's another graph that has 7 vertices, and here's another one that has 10 vertices. Here's another one with 10 vertices, and here's another one with 10 vertices. So these are all graphs that I just showed from the 64. You guys see any patterns here? Well, certainly from the first 4, you see how there's this like K4 in the middle. There's this complete graph of 4 vertices. And then you have these wings on the side that are like, this is like a cycle of length 3 with vertices 1, 2, and 3. And here's another cycle of length 3. This one's very similar. You have a K4 in the middle. Now you have a cycle of length 5 on the left and a cycle of length 3 on the right. Here's a K4, cycle of length 7 on the left, cycle of length 3 on the right. So K4, you have 2 cycles of length 5 on each side. And here, this is similar to this first case, except now there's 2 K4s spaced apart in the middle. And then now you have your cycles on the side. So you might ask, can you generalize it where you have some number of K4s in the middle with odd cycles at the end? And it turns out, yes. So here's an example. And basically, I wrote code to generate these for whatever size you want. And I simulated them. And basically, for all the ones I simulated, you have equivalent quantum walks if you start at one of the 2 ends. So here's an infinite family of graphs. Here's another one, family 2. So this is the smallest example. This one has 5 vertices. Here's one with 7 vertices, 9 vertices, still 9 vertices, and now 11 vertices. So you can see the pattern here where you get this shape here. I'm calling this a tail because this one to me kind of looks like a fish for some reason. Like this is like you imagine an eyeball here, and this is the tail of the fish. So imagine there's a tail and you have this odd cycle, tail with an odd cycle, tail with a bigger odd cycle. And it looks like we can actually stick in K4s too between the tail and the head of the fish. Here's a K4 between the tail and the head of the fish. And it turns out this generalizes. So if you have something like this where you have 2 K4s even between the tail and an odd cycle, that again, you get equivalent quantum walks if you start either at this end or either of the two tail fins. And again, I generally coded generate these, so whatever sizes I've tried, you get equivalent walks. So there's no proof of this in general. Third family looks like this. So here are a couple of graphs. And here we kind of get, I guess we have two tails. So this is not a fish, and this is a really weird fish. So here's like a tail on the left, a tail on the right. Here is a tail on the left, tail on the right. And you can see how we can just kind of separate them further and further. So this generalizes. So you have these two tails, and then with these long bridges between the tails. Yes, someone commented, it's a fish with no head. And so this is another family. So again, no matter what size I generated, you get equivalent quantum walks when you start at either of the four fins. Fourth family, we have these two graphs from the 64 from before. So if you look on the left here, these white vertices in the middle, this is a C3, it's triangle, right? It's a C3. Over here, these white vertices, this is a C4. So we have a cycle in here. And then it's surrounded, in this case, by 5 vertices. This case, it's surrounded by 6 vertices. And the outer vertices are adjacent to all of the white inner vertices on the inside. Out here, you see this is adjacent to all of the white vertices inside. So it turns out that this generalizes. If you start with any cycle inside and you have, so if you start with a cycle of m vertices inside, outside you have m plus 2 vertices that are adjacent to everything inside, that you get these that this supports equivalent quantum walks. And so there's a picture of that. That's a little bigger one. So again, I wrote code to generate these. Here's family 5. There's a bunch of graphs here. Let me show you these. Okay, so this is interesting. So I pointed out earlier when we looked at the fact that vertices 1, 4, and 5 are, I think, was it co-spectral? That's the term that someone mentioned. So you see how, again, vertices 2 and 3 are here. And then you see how 1, 2, and 3 is a triangle, right? It's a cycle of length 3. 2, 3, and 4, that's another cycle of length 3. And 2, 3, and 5, that's another cycle of length 3. Over here, we have a cycle of length 7, and then a cycle of length 3, and then another cycle of length 3, where they're sharing these two vertices. Here we have a cycle of length 5, another cycle of length 5, and a cycle of length 3, where they're sharing two vertices. Cycle of length 9, and 2 cycles of length 3 for this tail. Cycle of length 7, cycle of length 5, cycle of length 3, and these are 3 cycles of length 5. So it looks like if you have 3 odd cycles sharing 2 vertices, that this is a family, and that's true. So here's a giant example. And no matter what I generated, we get these equivalent quantum walks. All right, family 6 out of 8. The next one actually just comes from these two graphs. So if you look at this graph on the left, which was the smallest graph, which has 5 vertices, where there's equivalent quantum walks, you see how if you double the graph and you connect each vertex to its twin, that you get a bigger graph with equivalent quantum walks. And so this graph product, I looked at Wikipedia to see if this was a graph product, and I realized it was. This is the Cartesian product of the original graph with K2. And you guys would know what that actually means much better than I would. But basically, this always works. So if you take any graph and you take the Cartesian product of it with K2 to get its doubled up graph like that its doubled up graph also supports equivalent quantum walks. So I did this with all 64 graphs. And then with the new doubled up graphs, I did the Cartesian product again to get even bigger graphs, and it still worked. And I did it again to get even bigger graphs. So basically, as long as I take the Cartesian product of a graph with K2, I get a new graph with an equivalent quantum walk, with equivalent quantum walks. All right, family 7. It's actually just these two here. So you see how you get these squares on the left, in the middle you get an odd cycle. So basically you can generalize this. You have 2 squares on the sides, and then you get an odd cycle in the middle. So that's and then the final family that I was able to identify comes from these. So if you look at this graph with 5 vertices, I'm going to interpret it a little differently now. You see 2 and 3, this is a complete graph of length 2 or size 2. And then it's surrounded by 3 vertices, 1, 4, and 5, that are adjacent to both vertices of the complete graph. Here in this next graph, we have a complete graph of 3 vertices. It's surrounded by 5 vertices in red, and these 5 vertices are adjacent to all 3 vertices of the complete graph. Same thing here, we have a complete graph of 4 vertices in the middle. It's surrounded by, 7 vertices that are adjacent to all 4 vertices of the complete graph. And so that generalizes actually to whatever size you want, and on everything I generated and simulated, you get equivalent quantum walks. And so basically what we showed is that there are irregular graphs where the Laplacian and adjacency quantum walks are equivalent. They have the same probability distribution for all time. We only proved it for the 5 and 6 vertex cases, but hopefully the existence of those convinces you that the numerical ones are probably right. Of course, it's going to take mathematicians like yourselves to prove those. So yeah, we found 64 graphs or irregular graphs, irregular connected simple graphs, whatever adjectives you want to add in there, with 11 vertices or less where you get these equivalent walks. From that, we found 8 families of graphs. And there's a ton of open questions from this because this kind of opens up a whole new avenue of things to investigate. One is obviously, are there other families besides those 8? And I'm sure there are. I'm not clever enough to think that I've caught all of them. Another thing is whether or not all of these graphs with equivalent quantum walks, whether they fall into some type of family or if there's any graphs that don't fall into any family. And I guess to know that, you need to know what the families are. So I don't know. Another thing is we saw that as the graphs got bigger, then we started to find more graphs. So for 4, 5, 6, for 4, 5, and 6 vertices, we only found 1 graph each. And then from there, we started finding more and more graphs, and there's 4 graphs, and eventually we had like 28 graphs when there were 11 vertices. So with 12 graphs, are there even more? 13 graphs, are there even more? Or like, does it at least just not go down? Does it monotonically increase? And even more specifically, given the size n, how many graphs are there? So if there's 12 vertices, how many irregular graphs support equivalent walks? I don't know. I only simulated up to 11. Another question is other initial states. So we assume that you just start at 1 vertex. What if you start in a superposition state? And so actually, when I first did my simulations, I actually had a bug in my code where instead of starting at a new vertex, it actually added to the existing starting vertex. So basically, I was walking in superposition and just adding vertices. And there actually were some graphs that popped up as equivalent. And so basically, there are some equivalent graphs. I didn't save them, but there are some equivalent graphs where you can start in some superposition state and you get equivalent quantum walks. And so that's another thing one could explore, although I think starting at 1 vertex is probably going to be the easiest in terms of making any analytical headway. And then a final open question is to account for different jumping rates. So in one case, the Hamiltonian is equal to the Laplacian, and the other case, the Hamiltonian is equal to the adjacency matrix. Remember, the Hamiltonian has a physical meaning. It's the total energy of the system. And so if the Laplacian and the adjacency matrix have different norms, then they're actually using different amounts of energy. Or another way to put it is that they have different jumping rates. So the one with a bigger norm, it's using more energy and it has a jumping rate that's higher. And so if you actually want to walk these 2 types of walks in the same manner at the same pace, you actually have to kind of rescale time for them. And so that's going to completely change then which graphs would support equivalent walks. And so these are just some ideas that I have for some open questions. And for all of these graphs and all the proofs in more detail, you can check out our preprint on the archive. We just posted it 2 weeks ago. And thank you for listening.